You hear the term machine learning thrown around all the time, right? But what does it actually mean? Well, it turns out it's not just one single thing. It's this huge field where an algorithm can follow one of three very different paths to learn. So let's dive in and demystify how a machine goes from knowing absolutely nothing to making some seriously intelligent predictions.
So let's start with the most basic question of all. How does a machine actually learn? I mean, is it just memorizing a bunch of facts? Is it somehow thinking? The reality is a really cool shift away from the old school way we used to tell computers what to do. For decades, programming was all about giving a computer a super strict set of rules. If this happens, then do that. Humans had to write every single instruction by hand. But machine learning, it completely flips that script. Instead of feeding the computer rules, we feed it data. Tons and tons of examples. And the machine's job is to figure out the rules for itself by finding the patterns hidden inside all that information. And that brings us to what is, without a doubt, the most important question you have to ask first. If the machine learns from examples, then the kind of examples you give it is what decides everything. It determines which learning path you're going to take. In machine learning, it all starts and ends with the data. Okay, our first path is the one you'll run into most often. It's called supervised learning. And honestly, the best way to think about it is that we're basically giving the machine a study guide that already has a complete answer key in the back. The secret sauce here is something called labeled data. What that means is every single piece of data we give the model is already tagged with the correct answer. We show it a picture of a cat, and it's literally labeled cat. A picture of a dog is labeled dog. The model's entire job is to just find the connection between the input, the picture, and that correct output label. Now, supervised learning usually handles two main types of problems. First, you've got classification. This is all about sorting things into neat little buckets or categories. Think, is this email spam or not spam? Then you've got regression, which is about predicting a specific number on a continuous scale, like what will be the selling price of this house. One sorts, the other predicts a value. So we've trained our model with the answer key, and it's starting to make predictions. That's great. But how do we know if it's actually any good? How do we grade its performance to see if it really learned something useful? Well, the most common place to start is by measuring its accuracy. And it's pretty much exactly what it sounds like. It's a simple score that tells us what percentage of the time did the model get the answer right. You just take the number of correct predictions and divide it by the total number of predictions made. Seems simple and intuitive, right? But, and this is a really big but, high accuracy can be a total trap. This happens a lot when your data is unbalanced. For example, imagine you're building a model to detect a super rare disease that only affects, say, 1% of the population. A lazy model could just predict no disease every single time, and guess what? It would be 99% accurate, but it would also be completely, utterly useless. This is a perfect example of why accuracy is a good start, but it definitely doesn't tell you the whole story. All right, let's head down our second path. Unsupervised learning. This is where the game completely changes, because now we take away the answer key. This time, we're asking the machine to just dive into a massive ocean of data and find the hidden patterns all by itself. With unsupervised learning, we're dealing with unlabeled data. There are no right answers provided. The Lego analogy is perfect here. It's like dumping a giant bin of mixed up Legos on the floor and just saying, okay, sort these. There are no instructions, no picture on the box to follow. The algorithm has to figure out which pieces belong together on its own. So the main goal here is to discover that hidden structure in the data. The most common way this is done is through something called clustering, where the algorithm groups similar data points together. A classic real-world example of this is customer segmentation. When a company wants to find natural groupings of its customers based on their buying habits. The cool part is, the model can find these subtle patterns that a human analyst might never, ever spot. So, how in the world do you measure success when there's no right answer? Well, it all comes down to the quality of the groups it creates. A good unsupervised model is one that does a great job of putting very similar things into the same bucket, while at the same time making sure that different buckets contain things that are very, very different from each other. And that brings us to our third and final path, which is really in a league of its own, reinforcement learning. This isn't about labeled data, and it's not about finding hidden patterns. This is all about learning how to make the best decisions through pure trial and error.
Yeah, reinforcement learning is a totally different way of thinking. Imagine an agent. It could be a robot or maybe an AI playing a video game. This agent lives inside an environment, and every time the agent takes an action, the environment gives it some feedback, either a reward for doing something good or a punishment for doing something bad. The agent's one and only goal is to figure out a strategy that gets it the most reward possible over the long run. It all works on this fundamental feedback loop. Step 1, the agent looks around and sees its current situation, or its state. Step 2, based on that, it tries taking an action. Step 3, the environment immediately responds with a reward, positive or negative. And finally, step 4, the agent lands in a new state. This loop just repeats thousands, sometimes millions of times, until the agent slowly learns which actions lead to the biggest long-term payoffs. This whole process creates this fascinating central dilemma in reinforcement learning. Should the agent exploit what it already knows, stick to the moves that give it a pretty good guaranteed reward? Or should it explore by trying new, risky actions that might lead to a total failure or just maybe a much, much bigger reward? And this chart right here shows you the answer so clearly. Look at the brown lines. Those are the greedy agents that only exploit what they already know. Sure, they get a decent reward pretty quickly, but they hit a plateau and never get any better. Now look at the blue lines. These are the agents that are willing to explore. They actually do worse at the beginning, but by trying new things, they eventually discover way better strategies and end up with a much higher reward in the long run. Exploration is the absolute key to mastery. Okay, we have walked down all three paths: supervised, unsupervised, and reinforcement learning. Phew! Now let's bring it all back together for a final, crystal clear summary. This table is pretty much the ultimate cheat sheet. Supervised learning uses labeled data with an answer key to predict things, like in spam detection. Unsupervised learning takes unlabeled data to find hidden patterns you didn't know were there, perfect for customer segmentation. And reinforcement learning learns from trial and error rewards to master a goal like the famous AlphaGo that learned to dominate the game of Go. The path you choose really just depends on two things: what kind of data you have and what you're trying to achieve. Now, I know what you might be thinking. There's one more huge buzzword we haven't talked about: deep learning. Is that some kind of secret fourth path? Where does it fit into this whole picture we've just painted? And the answer is actually pretty simple. Deep learning is not a fourth path. A better way to think about it is as a super-powered vehicle, like a Formula One race car. It's a specific, really powerful tool, an artificial neural network, that can be used to tackle problems on any of the three paths we've talked about. You can use it for supervised, unsupervised, or reinforcement learning. It's the engine, not the road. So, at the end of the day, understanding these three paths separately is just the beginning. The real, mind-bending future of AI is what happens when these paths start to converge. Just imagine an AI that uses unsupervised learning to find strange patterns in medical scans, then uses supervised learning to predict a disease based on those patterns, and then uses reinforcement learning to help a doctor choose the absolute best treatment plan. That convergence, that's what's going to define the next decade of artificial intelligence.